Okay, is the presentation.
Yes.
So, talking about standardization. So, I am Mirco. I am a research engineer, Department of Mapping, Localization, Navigation at Robert Bosch GmbH in Renning in Germany, and I'm actually working in the field of robotic navigation and SLAM. And today I want to talk about the unification of SLAM with this presentation that is titled Standardizing SLAM, Exploiting Recurrent Patterns for Modularity and Behavioral Robustness. So this is more an internal representation of the map to be standardized, but maybe it's a task very big. So this work is part of my PhD studies, which is the result of a collaboration between Bosch and Sapienza University of Rome, where I was kindly supervised by Professor Giorgio Grisetti. So if you see some parallelism between what this talk and what he said, it's his fault. And by the way, let's start with the presentation. And so I bet that every one of us agrees on the importance of the map in every real world robotic field. Otherwise, we wouldn't be here at a workshop called "How Good Is Your Map?" So it is a matter of fact that the increasing request of self-driving vehicles and service and customer robotics, such as vacuum cleaners, lawnmowers, and the necessity to reach and explore dangerous environment like in research and rescue missions or extraterrestrial one, or even the desire of augmented and virtual reality applications for entertainment or assistance are widely spreading in latest year. These and many other applications have in common the need for an internal representation of the surrounding environment and require knowing the pose of the robot within this environment. In view of this, researchers during last decades invested substantial effort in finding solutions to this problem, converging in the field named SLAM. There is no need to explain to this audience what SLAM is, but just to be on the same page, I define SLAM as the process in which an agent is required to create a map of the surrounding environment thanks to its sensors, while estimating its own pose in the created map. A digital representation consisting of retrieved environment and the trajectory of the robot within the map. Nowadays, the trending SLAM problem formulation involves a graph-based estimation where each variable is the node of the graph and the factors stands on the edges connecting those variables. Literature usually splits the SLAM architecture between the front end, which is responsible to build the graph, and the back end, which instead performs the graph optimization in order to find the best configuration of the nodes that fits the measurement provided by the front end. Literature shows us a vast amount of SLAM approaches that are capable of impressive results both in accuracy and precision. However, there is no standardization in SLAM, meaning there is no defined taxonomy and modularity. And this brings the inability to combine different approaches in an easy way. Usually, novel SLAM systems are built as ad hoc holistic solutions for some specific dataset, which might not represent the variety of situation of real-world scenarios. Therefore, these systems will not handle properly challenging conditions which are not part of those datasets. For example, kidnapping, sensor failures, perceptual aliasing, and so on. Another flaw, in my opinion, in the SLAM community is that there is a little presence of multi-sensor SLAM systems. This kind of system brings the robustness, the more robust estimation, leveraging data coming from redundant or orthogonal sensor cues. Luckily, in latest years, the literature has been enriched with some flexible multi-sensor SLAM frameworks such as MOLA, EarthUbMap, MapLab. And finally, state-of-the-art systems are unable to readily deal with real-world unforeseen events, as they are not present in those datasets we were talking about. Such events are addressed in an incremental way at occurrence. That is, each time a given event impacts the performances of your SLAM run, the developer addresses that specific circumstance without caring much in reshaping the code for a more elegant solution. And the idea, our idea, is to create a single SLAM system able to work in different configuration, like the one shown in the figures, that could be dense, sparse, 2D, 3D, and which are at the same time able to react to events. We address the aforementioned problems exploiting an unifying approach. So as a first step, I will present a fully configurable and flexible SLAM architecture, which I'm at standardizing single and multi-sensor SLAM by creating a taxonomy for a generic SLAM system. And with this architecture, the user can combine processing modules in a plug-and-play fashion, relying on the set of off-the-shelf modules and interfaces built with reusability and efficiency in mind. And in the picture is shown a generic SLAM pipeline from the collection of the raw data to the optimization of the process. Then I will introduce what we call the SLAM state machine. That is a behavioral controller, and we can see SLAM as an interconnection between some actors and a director, where the actors are the processing modules that are defined in the taxonomy, the 1% that we've seen before in the plug and play SLAM, and the director is instead the modal controller, which guides the data flow through the system. Researchers actually mainly focus their attention on the structural aspect of SLAM, looking for the best performing algorithm. Instead, most of the time, they leave aside the modal aspect, which is usually implemented as an underlying hidden controller with a bunch of conditional statement in the code. In conjunction with the previous work, we wanted to give the same relevance to both of these aspects by creating a taxonomy for the SLAM architecture, which fits in the model controller, such that the system is natively capable of facing a wider range of events with the state of the art. With respect to the state-of-the-art SLAM systems. So let's start with the actors of our game that are the models of our SLAM system. So the goal of a SLAM system is to jointly estimate both the trajectory of the robot and the map of the environment from the sensor reading. In modern SLAM system, these two quantities are represented as variable in a factor graph. Measurements deducted from the sensor are encapsulated by factors in the graph, and to exploit the temporal and spatial locality of the SLAM process, our system organizes this graph into local maps. A local map is just a portion of the graph capturing some specially close elements. So the aim of our system is to create interface for modules of a generic SLAM system. Model systems have a pretty standard structure for how the data is processed, and their workflow can be summarized in 4 core points. As a first step, we need to convert raw data into a format that is feasible for the rest of the system. For example, we can extract the point cloud from a range vector, and this is done by the raw data preprocessor. Then the system needs to estimate the relative motion between two comparable entities, which can be like two subsequent measurement or the map and measure. And this task is accomplished by the aligner. And in our implementation, this model is agnostic to the current state of the system and operates only on its input. Relying on the aligner, a trajectory of the robot is created and consistent measurements are embedded into a map thanks to the tracker. And finally, a macro module called GraphSlam optimizes the map on the constraints given by the detective loop closures to produce the most consistent representation of the environment. GraphSlam is also in charge of creating a new local map that will be filled by the underlying submodules, for example, by the tracker. In our taxonomy, we also introduced some support models which help the modularization of the system. For example, we have the correspondence finder, which seeks for association between two comparable entities, the map merger that incorporates new measurement in the local map. Then we have the loop detector and validator in charge of finding loop closures and reject false association. And in the end, a global optimizer is needed to refine the map. One can change the implementation of these models on the fly, resulting on a different flavor of the SLAM pipeline, or realize different functionalities to combine by combining them in different ways. So what we saw until now is a generic SLAM system architecture. And now we focus more on the multi-sensor aspect and the way we implemented it in our framework. First of all, we carefully design a suitable data structure to efficiently store and query multi-sensor data. We achieve this by implementing an introspectable and serializable data structure called property in C++, which can contain an arbitrary data type and is collected by a dynamic property container. The power of this tool is that thanks to the native introspection, dynamic property containers are able to retrieve a specific property at runtime just using the property name. We exploit this flexible data structure, for example, for multiple queues in the raw data preprocessor or to store different layers of a local map. Leveraging this dynamic data structure, we have to remodel some of the processing modules in before to comply with it. So in the whole architecture, the only modules that need to be reconstructed are the aligner and the tracker that works directly with these dynamic property containers. To deal with multi-sensor, we introduced the concept of slices, that is a partial processing unit module, which handle specific queue by defining a set of traits. In fact, our multi-aligner, multi-tracker user use several slices to perform per sensor processing. Here in the slide, we can distinguish an arbitrary multi-aligner with two slices and with three slices and two slice multi-tracker. I want to stress out, however, that each slice is contributing in estimating a single quantity. In the case of the aligner, it's the ego motion of the robot, while in the case of the tracker is the local map and the trajectory of the robot within it. So we validated our result both in 2D and 3D datasets. For example, for the 2D case, we set up some experiments in simulated and real world. In the table, we show the result of 4 different runs in simulated environment using 2 lasers and wheel odometry. And on the bottom instead we have a qualitative comparison between our approach and another mapper on a robot with 2D LiDAR and with a single 2D LiDAR and wheel odometry. For our 3D experiments, instead, we relied on the use of 3 well-known datasets for Visual SLAM, which are Kitty, ICL, and UROC. And as we can read from the table, our approaches reach results comparable to the state of the art. And now we present the director, which is the SLAM state machine, a behavioral controller that allows to handle unforeseen event. And for doing that, I will start with a simple toy example in which a user buys its brand new Bosch vacuum cleaner, obviously, and place it inside of its house, composed by 3 rooms. Impersonating the robot, we would like to create the map of the house. Our SLAM system is decoupled from the navigation subsystem. Then the motion controller decides where to go. It's not something that SLAM should handle. Once the robot is turned on, first thing it needs to be is to do is some initialization of the system, loading of configuration parameters, maps, some kind of calibration, something that could be, and once it's initialized, it starts its mapping session. of the unknown environment. The planner now decides that it wants to go toward the corridor, and the robot turns on the spot, understanding that it's an already known environment, so it avoids to map it again, and just localize in the previous map. Once the robot reaches the corridor, it enters and creates a new map for the area. At a certain point, it can happen that due to some kind of sensor failure, the robot gets lost, and in the meanwhile, the motion controller goes a little bit toward the corridor. As soon as it is able to map again, the robot starts a new mapping session, storing the previous one, and in the meanwhile, it's also try to relocalize in the stored map, checking for already known places, and it continues its trip, reaching the door of room 2. So what happens in this case? Unfortunately, the entrance of room 2 is very similar to the entrance of room 1, producing some kind of false loop closures measurement due to some perceptual aliasing that brings inconsistency to the map. So now the robot believes to be in front of room 1, and the navigation algorithm decides to re-enter the room. So the current measurement of the robot sensor and the actual expected measurements highly differs one each other, and this could be a symptom of some kind of wrong loop closures and can be detected. Some recovery routine and possibly the rollback of the data, the robot is now able to create a new mapping session without map corruption. And now the robot can continue the journey to the flat and reach room number 1. What happens in this case? The robot now is correctly able to localize in the previous map and merge it with the actual one. Then the user decides at a certain point to bring the robot inside of room 3. So the behavior is always the same. When it is able to map it again, it stores the previous map, starts a new mapping session, try to relocalize in the previous map. Upon successful relocalization, the map will be merged. These examples show how the robot should behave in a natural way, as me, as a human being, would behave in the same situation. The next step is to formalize this behavior such that it can be executed by a real robot. In the first phase of our work, we decided to understand how other approaches would handle challenging situations. So we conducted some kind of structural analysis of the code to understand how state-of-the-art SLAM system works are composed. Then, via closed-box analysis, we estimated the behaviors of their system on a standard dataset with some artifacts introduced to make them more challenging. And from this, we were able to construct the underlying state machine of the considered SLAM system. As expected, all of them focus more on the precision and accuracy of the SLAM run, neglecting real-world scenarios. Results of those studies on how a system should behave can be summed up in the following point. So, whenever the robot gets lost, it should store the map and simultaneously map the new part and try to relocalize among previous maps. There should be a way to autonomously switching to localization mode to save resources. And at the end of the SLAM run, it could be useful to refine the map via a batch optimization. And so we formalized this via an UML state machine that allows some nice features like hierarchical and orthogonal states, some actions predefined at entry, exit, and while in the state, and internal transitions. Finally, I was able to synthesize my SLAM state machine, keeping in mind all the information gathered from the previous studies. And with this implementation, we achieved the desired behavior from the case study. So we hypothesized that by addressing the modal aspect of the SLAM system, we can enhance SLAM robustness. To validate this hypothesis, we conduct 2 experiments in which we evaluated the proposed state machine against the SLAM systems of the state of the art, comparing both behavior and resulting map. First, a theoretical experiment was conducted where, thanks to the closed box analysis done on the state-of-the-art system, I demonstrated in the vacuum cleaner study case that all the competitors perform disruptive or incorrect behaviors at some point during the run. And the table summarizes the behavior of the systems according to the reconstructed state machines. As long as the system produces consistent results, we highlighted the corresponding cells on the table. It is therefore plain to see that all the competitors incur in wrong state transition handling before the end of the run. For example, as soon as OrbSlam2 loses track at point 4, it always try to relocalize in previous map, discarding all the upcoming measurements. And in the end, okay. In the end, we also conducted a qualitative experiment on simulated datasets running to the LiDAR SLAM system against. And the robot gets kidnapped and replaced twice during this run. As we can see in the video, albeit our state machine works on top of naive to the SLAM implementation, we are able to retrieve at least a topologically consistent with the ground truth. So we talked about this SLAM architecture and behavior and behaviors. We understood how to generalize the SLAM taxonomy. Unified architecture presented also a multi-sensor SLAM standardization, and in the end, we also showed this SLAM state machine that could be an elegant solution to handle unforeseen events. So, thanks for your attention, and please feel free to ask me your questions.
Thank you very much. Exactly, are there any questions? Magnus, I'm spotlighting you, so now you can talk freely.
Yeah, thanks. I think I totally agree with you, both that the taxonomy would make it much easier to plug and play different modules and try them out or combine them, and also that it's under research, this part with a state machine, that because you need to make decisions, right? What am I going to do next?
Absolutely.
But I was thinking, in your state machine, it seems like it's in control of the robot the whole time. So either you're doing exploration or relocalization or something.
Just a moment.
At least for a robotic vacuum cleaner, I'm thinking that usually what you do is either you're doing everything is going fine, so you're doing some other task like the actual cleaning, or you're maybe plowing a field or something, and the state machine for SLAM would just monitor it, and it would step in and take over in case you need to relocalize. So have you thought about the state machine having some states where the SLAM is actively controlling the robots, and some states where it's sort of standing back and allowing the robot to do the target work?
Okay, so let's say this was this is a first work on this field. Obviously, it's not meant to be working right now with with a real world within a real world scenario. And but thanks to the formalization of the state machine, but that is one of the several formalization that could be. I'm also thinking about having behavior trees in order to control the SLAM task. However, those formalization allow us to expand the set of features, set of actions that a robot can do. So to my knowledge, yes, we can think of enlarging this representation in order to deal with other macro modules such as the navigation one or things like that. Otherwise, we can keep SLAM as a single process that produces our map, our trajectory, and based on what the robot sees, all the other modules such as navigation will infer what to do.
Mm-hmm.
I don't know if I answered the question.
I agree. I'm just saying that sometimes if you get lost, SLAM, I guess, needs to, or this statement needs to take over. You need to actively relocalize, but in many cases, you can just passively observe and maybe do some optimization of the maps and loop closure. So I still think it would be an interesting extension if you would categorize that some states here are passive and some are active. So you actually need to take over from the target behavior and focus the whole behavior of the robot on relocalizing, because those are two different macro states to me.
That's a really good point. Yeah, I agree with you that not all of the tasks that are all the states that are in this machine are equally let's say equally not important, but
at least not equally active in driving the robot. Sometimes we can just monitor.